Elon Musk is building Optimus, a humanoid robot that can do anything you want. But Elon is a busy man. He's building rockets, going to Mars, operating Doge, and even putting chips in people's brains. Since he's busy with all that other stuff, we're gonna build Optimus so Elon doesn't have to. I've built robots in the past, but this is gonna be my most insane project yet. I have no knowledge of modern hardware, manufacturing, electronics, or anything you need to build a modern robot. While mindlessly scrolling Twitter one day, I found out about this guy named Levick. He's built this unbelievable humanoid robot without legs that can move according to when he moves his arms. And the craziest part is, he's open sourced the entire robot. So we're gonna build our robot off of this base. Now that we've got a base design of the robot to work with, we've got our first major problem. How do we make the parts? It looks like the original design calls for 3D printing them, but that sounds crazy to me because I've had nothing but awful experiences with 3D printing many years ago with the chessbot. So with this history, I was a bit skeptical about 3D printers, but I decided to give it another shot and bought a Bamboo Lab 3D printer because of some good reviews online. My first reaction is this printer is incredible. It managed to print multiple pieces on the arm flawlessly on the first try. We then bought some tools, motors, and thousands of screws and started to turn our little shoebox apartment into an advanced robotics factory. Here's how the robot will work. There are 3 servo motors near the shoulder area, allowing the upper arm to have 3 rotational degrees of freedom. Each servo motor is going to have 30 kg/cm of torque, allowing each to hold a mass of 30 kilograms 1 centimeter away. However, the design also calls for a planetary gear system with a gear ratio of 3:1. This allows each motor to get 90 kg/cm of torque at the cost of slowing down the motor by 3 times. That's not much of an issue though, because the motors are already very fast, and we'd like the robots to be able to lift heavier objects, such as its own arm. While putting together the shoulder though, we ran into our first snag of the project. Instead of dual shaft motors, which the original design called for, we accidentally bought single shaft motors, which don't work well for robotics. This was a big mistake that cost us 7 days and over $250. Lesson learned. The lesson was not learned. We got the new motors and we put together the entire shoulder and upper arms. The 3D printer was working overtime. We were so impressed, we bought 2 more printers and had them also working 24/7. We had our fair share of printer mistakes, but those are mostly because we had redesigned the CAD poorly and didn't use supports in some areas. But after a week, we had the full torso and arms working. Now it's time to connect the arms and torso and put the robot on the stand. The stand is created using 3 metal arms connected by a series of angle brackets, with the bottom torso of the robot slipping right inside. I originally wanted to see if we could complete this entire build without electronics in 2 months. So it's finally exciting to see that after 1.5 months, we're finally making real progress on the robot. With 2 weeks left in our goal, we spent day and night putting the robot together. My brother worked a lot on the arm pieces while I was busy putting together the head. And after a few days, we finally got the robot balancing on the stand. The original design was mostly fantastic, but there were a few changes we wanted to make it easier to manufacture. The first is the original arms are held together by friction, so we added screws so that they stay in without falling off and breaking. The second is the bottom of the torso was very difficult to screw in because of the orientation of the screws. So instead, we designed a square plate so we can drill the screws into the side. With about 1 week in our self-imposed challenge, I began to work on the hands. I wasn't fully aware, but I had the idea that the hands would be the most difficult part of this project. The human hand is actually pretty incredible and has a lot of functionality that we take for granted. Even something as simple as picking up a glass of water is very intuitive for us, but almost impossible for a robot without sophisticated controls. The hand works by rotating a small servo for each finger. The servo arm is connected to an actuator, which pulls a tiny ligament to curl all 3 sections of the finger at once. This allows for some basic grip, but we really need an opposable thumb if we want to grip more complex objects. The thumb is similar to each finger, but has an additional servo at the base to rotate and give the thumb its opposability. The hand is very difficult to construct, but it's worth it because it actually is able to grip things just like a human would. It's still rather rudimentary, but I think with enough work we can get a really nice complex robot hand. And of course, the hand also has the smallest parts, meaning they break easily, and it's very difficult to put them back together and often. Realistically, for a future version of this project, we'd use 3-finger hands as they're way easier to control. We finished the hands and screwed them into the robot, and with 1 day to spare, we had the initial design of our robot complete. Or so we thought. And this is where it started to go downhill fast. We bought 50 pulse width modulation motors instead of serial bus motors, which is required by the design. This means that the motors that we had didn't have encoders used to track the position, which is critical to control the robot. We really paid the stupid tax on this one. We were 1 day away from our self-imposed deadline, and now we have to spend almost $1,000 on new motors and have them shipped in over a month. Lesson actually learned this time. But undeterred, we placed the order for the new motors, and while we wait for those to arrive, it's time to work on the brain. To rotate the servos, the original design calls for a specific servo controller, but we're going to update this to include a Raspberry Pi so we can get more general functionality. The Raspberry Pi is an extremely versatile Linux machine, but we've also attached an AI chip and a cooler for better performance. Now with the servo controllers and the Raspberry Pi, we can control the robot and record the data to train AI functionality in the future. It's critical that we're able to record the robot's movement, because if we want this thing to work autonomously, it needs to perform the same action thousands of times, even hundreds of thousands of times, so that the neural network can learn what it's supposed to do correctly. It's, in a way, very similar to how the human brain learns. For the techies out there, we downloaded Ubuntu onto the Raspberry Pi and leveraged ROS2, which is a robotic operating system, in order to control the servo motors with code. Also, we're actually using a second Raspberry Pi and servo controller for the teleoperation. This allows the Pis to wirelessly communicate with each other, so we can send commands from the teleoperation controller to the robot. The original design was coded in C++, but because this is an open source robot, we decided to code this in Python so it's a little bit easier for new people to understand. So we've open sourced all of our Python code if you want to try this robot out yourself and build your own. With the brain set up, it's now time for some fun. Robots like to have fun too. So with the new motors in, the robot was looking good as new, and we dressed him up in some belated Halloween costumes. That is crazy. Alright. It's doing the Trump. As best as it possibly could. Oh, this is awesome. Oh, it's all intact. It survived.
It's time to do it!
You broke the hand. Well, that didn't work.
Well, earlier we couldn't get any footage of it breaking, now we're only getting footage of it breaking.
Yeah. With the robot fully constructed and the brain working, we finally got the robot to move. Kinda. The robot moves using a teleoperation controller. Made with similar servos and 3D printed parts, it allows us to control the robot using our own motion. Very nice, very nice. So we fired up the 3D printers again, and we actually bought 3 more 3D printers to make it go even faster. We learned a ton of lessons the hard way when building the original robot, so we're not going to make those same mistakes again when building the controller. Though I did have to pull an all-nighter to finish the controller because we were going to our parents' place for the holidays and weren't going to have access to our 3D printer. The robot is going to love the holidays with our parents. We strapped him in a seatbelt, safety first. So my brother is putting the seatbelt on the robot. Of course, by the time we got back, he was in a ton of pieces from being broken on the stairs, so we had to reprint a lot of parts. The servos in the controller send positional data to the robot's brain. The brain then transmits that signal to the servos in the actual robot. The challenging part is that many of the servos in the actual robot have a 3-to-1 gear ratio. This means that a lot of the positional data is going to be slightly mismatched, and we have to fine-tune it to make sure it's perfect. It's very easy to break the robot's arm when doing this, so we have to be extra careful. While my brother continues to work fine-tuning the controller logic, I'm going to be building the battery system. This bad boy is a 12-volt, 12-amp-hour lithium-ion battery. This means that our battery can draw 1 amp of current for 12 hours without needing a charge. A good way to think about circuitry is this diagram and this image here. We tested rotating all of the robot's servos at once and found that it draws about 2 amps of current, which means if all the servos are moving at once, the robot will have about 6 hours of charge. I designed a 3D printable battery pack to hold the Raspberry Pi, servo controller, battery, and other circuitry. The final piece we needed was a buck converter to transform the 12 volts from the battery to 5 volts, which is the amount of voltage required for the Raspberry Pi. And after that, we quickly finished securing the battery to the robot with a working circuit. My brother's been working tirelessly to perfect the fine-tuning of the robot's motion. What started as the robot contorting and shattering its own arm, now the robot is having perfect fluid motion. Ah, it's working. Hallelujah. There's no legs on the robot yet, but it's working absolutely amazing. A seriously huge shout out and thank you to Levick for open sourcing this robot. We'll have to keep building up this project and open sourcing our contributions to it as well. I hope you guys enjoyed this video, and if you want to check out a chess robot that I built 7 years ago, you can find that here. Sorry.